Okay, so my apologies for bringing you in here. We have some seminar over there. Just only today we're doing it here. So, but actually last year when I was giving these lectures on the quantum cohomology, some of you were here. You know, we did spend many hours in this room. So. Okay, so I did DG rings, modules over DG rings, some of the properties of modules over DG rings, and tensor products, homomorphisms, in this category of DG rings. So let us move to DG schemes. Okay. So definition. This is so by a DG scheme, we mean a pair which is denoted as x0 and O dot of x, where x0 is an ordinary scheme, and O dot of x is a sheaf of DG algebras, or sheaf of z-graded commutative DG algebras, and we did define these things last time. Commutative DG algebras on this ordinary scheme x0, such that the structure sheaf, the zero piece of the structure sheaf of x, notation O0 of x, this is the zero piece inside here, is in fact defined as the structure sheaf of the ordinary underlying scheme. Okay. And each OI of x is a quasi-coherent module, but is quasi-coherent. It's going to be sheaf, of course. Is quasi-coherent over O dot. So this is formally what a DG scheme is. Of course, I will give you an example. Affine, for instance, DG scheme. What does it look like? You know, I start from a DG ring. The spectrum of the ring gives you the affine scheme, or the DG scheme. But we will go to the example soon. So, but then this definition has two pieces. So this is part A of the definition. Part B. So now, a morphism. If I told you what the scheme is, then I tell you what the morphism means. A morphism F from X to Y of DG schemes. DG schemes is just a morphism. Just a morphism of DG ring the spaces. That is to say, i.e. morphism. Let's call that F0 from the underlying ordinary scheme X0 to underlying ordinary scheme Y0 of the schemes, together with the corresponding morphism of their algebras, corresponding with together with morphism of sheaves of DG algebras, which is pull back F upper star of O dot of Y to O dot of x. So this data of an ordinary scheme together with this DG algebra defines for you the DG scheme, and the morphisms are morphisms of the ordinary schemes together with the corresponding morphisms of DG algebras that you have on them. The DG algebra on the ordinary scheme is the information of course, the structure sheaf of the ordinary scheme plus other things. And these other things are quasi-coherent sheaves over
O0 of x.
Oh, sorry. Oh, yeah.
Sorry. So, do you require the ring to be co-connective? So, do you require the it's ungraded or z graded?
It's z graded.
But then the Artan minus a point would be an Artan scheme.
That's right.
Okay.
That's basically the example. Yeah.
But then how do you realize DG ring as a simplicial ring?
That we will need to do in detail.
Okay.
I will do it later. Yes. Actually, in some sense, if you look at the notes, we have so far done the derived stacks and the derived schemes. We constructed them off of simplicial rings. These are DG rings, much easier, maybe. But in general, different. But whether or not these two are related to each other actually has been worked out in detail in one of the papers of Kai Barrett. Maybe it's for the purpose of education. We're going to use that later. I will show you. But I didn't have it prepared for today. Let's just define things first. Okay. So this is that. And so this is a morphism in the DG scheme category. Now, by a graded scheme, we mean a DG scheme. DG scheme X in which O dot of X, has trivial differential. This is what we call gradient. It just has a trivial differential. Any ordinary scheme will be considered as a DG scheme. DG scheme with trivial grading. And differential. So let's take the structure sheaf of some ordinary scheme. It is of course a DG scheme because it has an underlying regular scheme, and then you can think of it as a complex with trivial pieces other than degree 0 piece and the differential also being the trivial differential. But in general, a graded scheme is not as simple as this one. This is the one that embeds the category of schemes in the category of DG schemes. But in general, a graded scheme means that you just delete the differentials. Non-trivial differentials. By above definition, for a DG scheme X, each D, which takes us from OI of X to OI plus 1 of X, each one of these things is OX0 linear differential. OX0 linear, and hence hi of O dot of x are quasi-coherent sheaves on x0, because each one of those things are modules over O0 of x, or x structure ring of x0. Then, well, you know, these are morphisms of OX0 modules, and so they remain as kernels, and images remain as OX0 modules, like the quotients. Okay, so that's that. These are quasi-coherent, and of x. So sheaves on x0. Okay, we define the degree 0 truncation. Degree 0 truncation of x to be the ordinary scheme, which is pi 0 notation. Pi 0 of x equal to spectrum of the H0 of O dot of x, which sits inside x0. Now, why is this the case? Because O dot of x is given as a some chain complex of modules over O0 of x, or O of x0. And taking kernels and co-kernels and so on, images, and taking cohomology also gives you quasi-coherent sheaves over modules over the structure ring of this guy, right? So every piece that you get after taking cohomology, including the 0 piece, will be a module over O of x0. Then you take the spectrum, so it embeds inside. The spectrum of H0 embeds inside the spectrum of O of x0, but that is by definition x0. So because O of x0 gets mapped to H0 of O dot of x, the spectrum of this thing gets embedded.
So sorry, could you please write the map on the coordinate ring? I got a little confused. So
you have O of O0 of x,
yes,
O1 of x, and you keep going like that.
Yes. But you have O minus 1. Do you?
Hmm?
Do you have?
You can have O minus 1 too, no problem. So you have this thing, right?
Yeah. Yes.
And these are quasi-coherent.
Yes.
Sheaves over O0. These are sheaves over O of x0.
Yes.
So taking kernels and co-kernels and the cohomologies also gives you.
I see. Thanks.
So you take H0 in this here and this degree in here, and then that gives you a module over here, of course. But then the spectrum of this module, and the spectrum of this thing by definition is the regular scheme. So, okay, so that's the this is by definition. This is the notation. Pi 0 of x is chosen to suggest analogy with homotopy groups. Homotopy groups in topology. And I put this comment here for now. But in fact, if I make the connection between simplicial derived schemes and the DG schemes rigorous, then you will actually see that the pi 0 is really, in some category, will capture exactly this piece. But for now, it's just a notation. We are just thinking of it as a notation. So, you know, this this ordinary scheme sits inside X0. This is interesting. Okay, maybe we'll use this later. Okay, so we have that. Note that for any ordinary scheme S, ordinary scheme S, we have some notion of a homomorphism in the category of DG schemes, because every ordinary scheme can be now realized as a DG scheme, of course. In the category of DG schemes, a morphism from here to here is realized by the homomorphism in the category of just the schemes from S to I 0. Now remark, H I of the complex O dot of X can be regarded as a quasi-coherent sheaf on pi 0 of X. Pi 0 of X. We have them. We then have two graded schemes naturally associated to a DG scheme X. One of the graded schemes, I should give you pairs, right? Each time I give you a graded DG scheme, I should give you pairs, right? So one of them is the one which I use the notation which I used before, X0 and O dot of X sharp. This is the one in which we forget the differentials. This is a graded scheme, it's true, because now this data is exactly by definition a graded scheme. So that's one of them. And the other one is the one that I use a XH is the pi 0 of X and H dot of O dot of X. Well, this is also a graded scheme. It's true because the maps between H dot of O dot of X are 0 maps. And that's a regular scheme. It just sits inside the underlying regular scheme X0. So you see, this is very interesting, right? The DG scheme, even when you want to, construct some kind of graded schemes out of it, you realize that it has more structure already. And you recognize it. Okay. So in fact, in the case of regular schemes only, these two things just match. A morphism F from X to Y of DG schemes we would call a quasi-isomorphism if the induced morphism of schemes f of h from x of h to y of h, if this one is an isomorphism. Okay. So now this is very interesting. In regular scheme theory, we don't have a notion of quasi-isomorphism between the schemes, but now because everything is constructed over DG rings, we do. This feature we also saw when we were discussing DG stacks and DG schemes over simplicial rings. Okay. So it's an isomorphism. So by D scheme, DSH, the category obtained by DSH, the category obtained by inverting all quasi-isomorphisms. Isomorphisms. By the way, note that this is quasi-isomorphisms of the schemes. DG schemes. Or the schemes. And calling it so let's say I want to fix my sentence. So we denote here, let's add that. We denote by DSH category obtained by inverting these things and call it right derived category. Right derived category of schemes. So very nice, right? So now we have the notion of derived category of not the modules over a scheme, but the schemes. It is suitable for taking derived functors on the schemes rather, not modules over schemes, but the schemes, this category, which corresponds to left derived functors at the level of commutative algebras. One of them is the opposite of the other, and so we are now defining something that really we haven't seen before. Right derived functor between the schemes. Okay, so we have this thing, and then now example. Because I promise I give you an example. This is the example. Okay, if A dot is a commutative, Z-graded DG algebra, like how we defined it last time. It has the graded pieces and the differentials. Then we have the DG scheme. You have DG scheme X equal to spec of A dot. Okay, defined as follows. Okay, so what is the meaning of this? The scheme X0, which is part of the data, is the spec of course, A0. So that's the affine regular underlying scheme of this. And now I should give you quasi-coherent sheaves over here. And the sheaf O dot of X is the quasi-coherent sheaf of DG algebras on the spectrum A0. So as modules, every piece is a module over is an A0 module. And the whole thing is a quasi-coherent sheaf of DG algebras. Okay, and okay, this is associated to A0 module AI. That's a DG ring that you start with. So every piece is a module over A0. So modules over AIs are also modules over A0. Okay, so that's that. The DG scheme X having the form spec of A dot will be called affine DG scheme. We will also write A dot rotation as the coordinate ring of the DG scheme X, and call A dot the coordinate ring. So coordinate DG algebra or ring. Coordinate DG algebra of X. What else? Well, you know, maybe as a just to complete the example, if E dot is a Z plus graded complex of finite dimensional vector spaces, then we have the DG scheme. We have the, you know, remind yourself of Hartshorne's construction of algebraic spaces out of say bundles, topological vector bundles and things like that. You always look at the dual of the dual of the bundle. Trivialization of the bundle, you can have coefficients. When you write down the bundle in coordinate charts, you have the coefficients, and those are elements of the dual of the bundle. And so the sheaf that you associate to a bundle is the dual thing. And from that, the spectrum or symmetric algebra of the dual sheaf gives you the space, algebraic space for that topological bundle. So this is that thing for vector spaces, right? So if you have some complex of vector spaces, then we have the DG scheme, which is denoted like this for complex of vector spaces. It is the spectrum of the dual thing, which is the linear DG space E dot considered as a DG scheme, as a scheme, as a DG scheme. So this is, of course, I mean, just the most simplified version of what I just said. Okay. So I think this is the nice example. So definition now.
Sorry.
Yeah.
Do you mean E2 or symmetric?
Yes, but that's what
what
you're
you mean.
right.
That's what I mean.
But remember that when I start from, okay, how do we construct the DG scheme? I mean, I made that as an analogy, but you need to pay attention to the definition of the DG scheme. You have a DG scheme. It's defined over a DG ring, and it has underlying regular scheme, which in this case is just a linear space, together with modules over the zero piece of the DG ring. All I'm saying is if you have a complex of vector spaces like this, the dual one will give you the ring with the differentials. And then the linear space, underlying linear space sitting in degree 0 is just a regular scheme together with the modules over the E0 piece in here. So that's what it is. I mean, this kind of notion of symmetric algebra is not in here because of the notion of the DG scheme also doesn't have that. Yeah. But I made that analogy because I wanted to remind you that now, for a complex of vector bundles, also you can construct some kind of a space out of it.
E dot is not algebra.
No.
So what do you mean by takes back?
Naively. So E0, the regular piece of E dot, is a linear space. It's an honest space, right? It's a scheme. It's a linear scheme. And then if you have a complex with the differentials, right, then those are modules over E0.
So is it the spectrum of symmetric algebra generated by E star?
E star.
Yeah.
Yeah. That's
what is the same.
Yeah, you can say that.
Yeah, that's
Symmetric algebra generated by
E0.
E0 only, and other is
Yeah,
just a
that's
full-black
right.
sheet corresponding to lines.
That's what you're saying.
Not the symmetric algebra.
Yeah, I think you're right. Yeah. It's just a linear space otherwise. Yeah. True. Okay. Now, definition, a DG scheme. DG scheme X is said to be of a finite type. Said to be a finite type if X0 is a scheme. Is a scheme of finite type. Scheme of finite type, and each OI of X, OI of X is coherent. It's coherent as a sheaf on X0. we say that X is quasi-projective. Say that X is quasi-projective DG scheme if it is of finite type, and X0 is a quasi-projective in the usual sense. So, well, by this, putting these in parentheses, I mean, you can have a notion of projective DG scheme or quasi-projective DG schemes. That really means that the DG scheme is finite type, and the regular piece inside it is quasi or just without quasi-projective regular scheme. Let's try some definition. Okay. Now, this is more or less the definition of DG schemes. And now, on these, we're going to study some further properties of DG sheaves. So DG scheme itself is given as some complex of sheaves over the reduced part of the DG scheme or regular part of the DG scheme. So now what is a DG sheaf? So definition, quasi-coherent DG sheaf on a DG scheme X is a sheaf F dot of O dot X modules with F dot of O dot X modules such that every Fi is quasi-coherent over O of let's see. If X is of finite type, okay, then we shall say that F dot, the DG sheaf, is coherent if every Fi is coherent over all that C. And if the complex F dot, and if F dot is bounded above, meaning that is to say Fi is equal to 0 for large enough files. So this is what the quasi-coherent DG sheaf and the coherent DG sheaf mean. Of course, sheaves over such a space could be captured by complexes. So, and you know, the reason that you get something like this, of course, is directly a consequence of the construction I did last time. You have a DG ring or algebra. We define the notion of modules over that algebra, and they were given by complexes, and you had this notion of ring structure which needed to be compatible to the differential, underlying differential of the algebra. This is basically that. This is a sheafified version of the definitions of modules over DG algebra. Okay. So you have this. If, like last time, if f dot is a quasi-coherent sheaf for DG, whenever I say sheaf, if I forget it, we really mean DG sheaf. If it's a quasi-coherent DG sheaf on X, then we have graded sheaves. This is exactly the sheafified version of the definition last time. We have this graded sheaves F sharp on X sharp and H dot of F dot on XH. So this is the graded scheme, which is given by looking at the pi 0 of your DG scheme together with the graded, piece in there given by H dot of OX, O dot of X. So these things, of course, will be moduled over H dot of OX because this thing is a module in the DG sense over O dot of X. So you have these two graded sheaves. Okay. And this is the one that you look at the O dot of X and you forget the differentials and the same thing. We did this for modules last time too. Just forget it. Last time we had this guy, but we didn't have this guy. This guy got added today. So both of them are graded because we have two graded schemes for a DG scheme. We also have two gradings for a sheaf on the DG scheme. So now, what about morphisms? Morphisms are morphisms of quasi-coherent DG sheaves, F dot to G dot, and homotopies between such morphisms are defined as was described before. As was described before. Same way that we had a morphism of modules over a DG ring A dot, and we had notion of this homotopy. So we had a morphism between M dot and M dot last time, and then we discussed that maybe we can have two morphisms F and G, and we defined the notion of homotopy between F and G. So same thing happens here. So this we defined before. Just a sheafified version. So a morphism F dot going to G dot is called quasi-isomorphism. Called quasi-isomorphism if the induced morphism of graded sheaves is an isomorphism. Okay, so these guys are modules over H dot of O dot of X. And they both live on XH. Like that. We denote by derived quasi-co of a DG scheme X, respectively derived quasi-co of X minus. The derived category, this is the honest derived category. The derived category, the one that we know, more familiar with. The derived category of quasi-coherent, respectively, of bounded above quasi-coherent sheaves. For a given DG scheme, you can define the notion of DG sheaves and the derived category of DG sheaves. Why? Because, like how we defined it last time, you have this sheafification of homotopies and quasi-isomorphisms between sheaves. So you invert those things, and naturally you land in the derived category of coherent sheaves and a DG scheme. So now you can see that again, this can get related to things that we did construct last time. Remember that we started from construction of simplicial pre-sheaves on underlying categories, abstract categories. We picked the base category to be category of commutative rings. And we had the notion of schemes, stacks, and modules or sheaves on them. Now, we kind of added the structure to the base. We looked at DG schemes and so on. So now you can see that you can define a notion of a derived category of DG sheaves over the derived category of DG schemes. That you can do. Whether or not it is helpful, that's a different story, but you can construct such a thing. Okay, so.
Just a curiosity.
Yeah.
So, is there a statement, something like if two DG scheme are quasi-isomorphic, they're derived? These two things are essentially the same, or something like that?
So maybe yes, their derived categories could be quasi-isomorphic, equivalent. The derived categories could be equivalent, not quasi-isomorphic, but equivalent. Yeah. Essentially, this is a little bit with kind of added structure of the notion that if I give you two schemes which are isomorphic to each other, then can you say that their derived categories are equivalent? It's actually true. But here, the notion of equivalence is a little bit less, more homotopy. I think, but I'm not sure, I should say. I cannot think of a situation where you give me two derived equivalent schemes and their derived categories are not equivalent. I cannot think of an example.
My curiosity is because I know you, in the end, you will go to it, but you mentioned in earlier lectures of why purpose of such notion.
Well, we don't work over the derived category of schemes, DG schemes. We will not. We will just fix a DG scheme with the honest, if we have DG schemes, we just look at the isomorphism of the DG schemes, but not weak isomorphism.
But I mean, if you run into a very bad scheme, like a singular scheme, do you want to take a quasi-isomorph in sense of quasi-isomorph in DG to make a better one?
No. If I have a very bad singular scheme, Then there is a notion of embedding it inside its derived enhancement, derived DG enhancement.
Derived DG enhancement.
In which case you have bad scheme and you embed the bad scheme into something nice, some nice smooth DG manifold.
Oh.
And then
Not taking quasi as one.
no. No. But that the smooth DG manifold that you embed this to, that you just work with that. You don't perturb that. You don't perturb it. You just fix it. Derived equivalence between schemes means that you construct the DG scheme and then you even perturb that further homotopically. I don't want to do that. You just so this example happens in the moduli spaces. You have a moduli space which is highly singular. You would like to define some object on this moduli space. One way of doing it is that you embed the moduli space inside this DG enhancement. That's just one derived smooth manifold. And on that thing you fix it, and on that thing you work.
In some canonical way.
Canonical way. No.
Even that is.
When you embed this thing inside its derived enhancements, that embedding is non-canonical. You can have different embeddings. So the DG enhancement is not unique. And this actually relates, later on relates to this thing that 2 years ago, if you remember, you were coming to my Gromov-Witten theory class, right? So we constructed these things, deformation obstruction theories, and we said that if I have a moduli space, the choice of deformation obstruction theory is non-unique. As soon as I fix one, I have one, a nice property, then for that moduli space I can calculate a bunch of invariants. Maybe for a given space I can have multiple obstruction theories. All of what we are doing here is basically along the same thing. This time, though, instead of finding the suitable obstruction theory, I find the suitable enhancement of my moduli space. This DG enhancement has a cotangent bundle, which after pulling back to the underlying singular moduli space gives you the obstruction theory.
Last class we defined homotopies between maps of DG modules.
Yes.
And in some sense, here when we're looking at the induced morphism of the graded sheaves, this is in the background.
That's right. That's right. That's right. Okay, so that is that. Now, definition. Let X be a DG scheme. A DG scheme of finite type. Finite type. DG vector bundle. DG vector bundle on X is a quasi-coherent sheaf F dot such that locally, and by that we mean on the risky topology, of, well, you know, every DG schemes has the regular underlying scheme, and that has the Zariski topology. So on that one, the graded sheaf F dot sharp of O dot X sharp modules is isomorphic to I'm writing down the condition for locally freeness, right? So a vector bundle in algebraic geometry is a locally free sheaf. And this is that. Is isomorphic to O dot of X sharp tensor over X0 with something like E dot, where E dot is a graded vector bundle on X dot. Last time we had the free module, and it was exactly like this. We say that if we have an O dot of X module, then it will be a free module if it is given by something like this time tensor over A0 with some graded module of generators. So this is basically the over all of X. This is the graded vector bundle this time. Okay. Graded bundle on X bounded above. Okay, so this is what a vector bundle on a DG scheme is. Remark, if X0 is connected, the sequence R, which is the R set of Ri's, which is the by definition rank of EI's, is uniquely defined by F dot and is called the graded rank of F dot. So of course, a rank of a complex is a tuple. We say that F dot has bounded rank if our i's are equal to 0 for some larger I. So because these are bounded above, so for very small i's, they stop becoming non-trivial. So in this case, the F star, which is homomorphisms from over O dot X modules from F dot to O dot of X, is again a DG vector bundle of bounded. Maybe you can call it F dot. I mean, this is just, or you can call it like this. Okay. So there is this lemma, which is the good. I mean, this is the following lemma. So let S be a. This is what you have seen before. Be a quasi-projective scheme, not the DG scheme, but just a regular scheme. Quasi-projective scheme. And then we know these are hold true. So for any F, the coherent sheaf on S, there exists a vector bundle. There exists a vector bundle E and a surjection Well, you know, this statement is about the fact that if you give me a coherent sheaf, it has a locally free resolution. So, so this is true, and B, for any quasi-coherent sheaf F on S, there exists a flat there exists an OS flat or S flat quasi-coherent sheaf E, and the surjection like that. Yes, this also we are aware of. So now, what you can do, the reason I'm mentioning this lemma is that you can extend this to the DG scheme. So now, based on this, there's a proposition which says that let X be a quasi-projective DG scheme. So that means that X is of finite type, and the underlying regular scheme on X is the quasi-projective itself, and O dot of X is bounded. And let F dot be a quasi-coherent sheaf on X, which is bounded above. Then we can have these two statements basically. So first is that F dot is isomorphic to a quasi-coherent sheaf E dot. Dot such that the graded sheaf induced by E dot such that E dot sharp is flat over O dot of X sharp. Okay. B, if F dot is coherent, if this is coherent, then it is quasi-isomorphic to a vector bundle. Vector bundle E dot on X. And the vector bundle is by the definition locally free on the DG scheme X that I just defined. So if it is coherent, it's quasi-isomorphic to a vector bundle. And if not, it's quasi-isomorphic to a sheaf of O dot S flat modules. So proof of this thing is by, proof is by above lemma. By lemma, applying lemma in each level, and using induction. So we do it for 0 modules piece and 01 modules piece and so on and so forth. And you use induction, and that's it. So that is that. What time is it? Let me see. I have half an hour. Okay, so let's continue. By the way, once again, if you're interested to read these things also yourself, majority of what I'm saying is based on the papers of Caprano and Silconfontaine, as well as the two papers of Kai Barrett. So in fact, I've mixed all of these three papers with each other. Some of the things I grabbed from Kai Barrett, some of them from papers of Kaplanov. That's very nice, really. And in fact, these two groups cite each other. The beginning of the class, though, was from the work of Toy. So now,
Sorry,
Yeah.
Just a point to make. When you say lecture bundle E dot, you do not implicitly mean it is bounded, or you already
no, we already had that in the
in the
yes,
definition.
yes.
And your X just a quasi.
In some sense, if it is coherent, it needs to be bounded. If it is coherent, it means finitely generated.
Yeah, I'm trying to compare this with usual situation. Usual situation, if things are this good, you need your scheme is smooth or some good, right? If your scheme, I mean, or in usual ordinary algebraic, if your scheme is very bad, then your coherent sheaf may still have a free resolution, but it won't be bounded.
That's right.
But you say here actually it's very strong, built into the language actually. It is already a possibility.
Wait, at least from one direction it will be bounded, right? So let me see.
You mean bounded below?
Bounded below. From one direction.
Actually, somewhere Artan use a bounded above, somewhere use a bounded below.
No, bounded below. It's always bounded from one direction. So.
But the other.
Yeah.
The other could go forever.
Let me see. How did I?
They require bounded above.
Bounded above, or bounded below. So from one direction.
One way bounded, but the other way could go forever.
Good.
Yeah, okay. Okay, that was all.
Yes, that's right. So bounded really here always is from one direction, one way or another, above or below. I mean, that depends on the choice. Okay. So derived tensor product. But that's a very good question. So derived tensor product. Let X be a PG scheme as O dot of X is a sheaf of commutative DG algebras. We can form the tensor product. Tensor product F dot over O dot of X G dot with G dot of any quasi-coherent sheaves F dot and G dot. For any quasi-coherent sheaves F dot and G dot in here. Well, we discussed this thing last time, module theoretically, what that means. Proposition, let E dot and G dot be quasi-coherent, bounded above DG sheaves. Bounded above DG sheaves on a EG scheme. On a DG scheme X, and suppose that E dot sharp is flat over O dot of X sharp. Suppose it's different. Okay, so then we have the converging, I'm not going to prove it, but it's a fact. We have the converging Eilenberg-Moore spectral sequence. Eilenberg-Moore spectral sequence of sheaves on X. And this Eilenberg-Moore spectral sequence is the one that defines for you the higher tors and so on. So it has second page E2, which is tor dot over H dot of O dot of X modules, H dot of E dot, H dot of G dot. And you know, this converges in the limit to H dot of E dot tensor with G dot over O dot of X. That, I mean, this is basically tor between E dot and G dot over O dot of X. So this is what it is. So what? There is this thing, and this allows us to define the notion of derived tensor product. So now definition, let X be quasi-projective PG scheme, and F dot and G dot be inside quasi-coherent sheaves on X, PG sheaves on X, bounded above. So maybe I can put something like in here to say that it is bounded above. Okay, so if I have this situation, the derived tensor product, then the derived tensor product, F dot, derived tensor product over O dot of X modules with G dot is by definition the usual tensor product E dot tensor over O dot of X with G dot, where E dot to F dot is any resolution of F by vector bundles, as any resolution of F dot, which is bounded above. This is essentially what we do in regular algebraic geometry too, that to calculate the derived tensor product, you replace one of the two by locally free resolutions. And then the derived tensor product is given by taking the cohomology of the complex. So far so good. Proposition in the situation of above definition, meaning that when X is quasi-projective and we have quasi-coherent sheaves, F dot and G dot, then we have two converging Eilenberg-Moore more sequences. More sequences. One of them is the one that's Tor dot. It's taking the Tor dot over O dot of X sharp modules between F dot sharp and G dot sharp. This in the limit converges to H dot of the F dot direct tensor product of O dot of X and G dot. And the other one is the Tor, again, dot over H dot of O dot X modules between these graded sheaves, H dot of F dot and H dot of G dot, which also converges to H dot A of F dot direct tensor product O dot of X, G dot. So this I'm not going to prove, but for proof of this actually, it's interesting. Look at, so for proof, look at this work by J. McCleary on Eilenberg spectral sequences over DG schemes. And I don't really use this in our construction because we don't use it, and it's an interesting fact. Somehow, homologically, in the level of direct tensor product, both of them converge the same thing. This is actually interesting later when we do derived intersections and so on. Okay, so there is this, and then let's see how much time. I want to see where to finish. Okay, 10 minutes. So let us now. We did all of this because, as you guessed, and as I mentioned, we are moving to the DG manifolds. DG manifolds and tangent complexes. Okay. Now, definition. DG scheme M is called smooth for a DG manifold if the following conditions hold true. One, that M0 is a smooth algebraic variety. Two, that locally on Zariski topology of M, and Zariski topology of the regular underlying scheme, M0 variety, we have an isomorphism. An isomorphism of graded schemes. Remember that the graded scheme is the one that I forget the differentials, or I take the co-amount. So graded schemes, O dot of M sharp. I would like it to be equal to the symmetric algebra over O of M0 modules of Q minus 1 plus Q minus 2, like that. graded graded sheaves. Graded sheaves where where Q minus I, now this indexing by minus, that's just a convention. Q minus I are vector bundles. Vector bundles of finite rank on M0. Now there is this important remark. So remark that the graded vector bundle, actually, yeah, never mind. This is suffices. Okay.
What is this?
Symmetric algebra over OM0 modules of vector bundles, not sheaves. So flat. So, okay, so now the dimension in this case, the dimension of DG manifold M is the sequence dimension of M equal to dimension of Mi. Okay, sorry. Di of M, like let's write it like this. Di of M. I need to define it. I bigger than 0, where D0 of M is the dimension of the underlying regular manifold, and Di of M is the rank of these bundles. Q minus I, for I bigger than 0. So, okay. And yeah, I think this is actually a good place to stop, because I cannot talk about cotangent sheaf and tangent complex. So what are we trying to do? We do this DG manifold, as I said, because the whole construction in this derived intersection theory and calculations over moduli space is that you find an ambient derived DG manifold that your moduli space, ill-defined moduli space, embeds into. And if you can suitably find it, then you can use the ambient space. It's a smooth, it has a cotangent bundle, which we don't have time to study. It's just a sheaf of differentials on it. And the sheaf of differentials on the ambient manifold eventually gives you a candidate for a perfect deformation abstraction theory over the original moduli scheme if you just pull it back. So you have two ways of dealing with this problem of doing intersection theory in algebraic geometry. One is that find a complex that satisfies nice properties and approximates the cotangent complex of the ill-defined space or variety or scheme or whatever. Or, instead of finding the suitable complex, find the suitable DG manifold, which this can be embedded to. And then naturally, as soon as you find it, the cotangent bundle of the ambient thing can give you what you want. So next time we do this, and then we are trying to move towards some of the examples. Derived Grassmannians, DG Grassmannians, things like that. And then derived Cote scheme. Because we would like to move to the moduli space of sheaves. So we do Cote scheme of Grothendieck, derived Cote scheme of Grothendieck, DG Cote scheme, and then modding out by automorphisms and going to derived moduli space. That's the derived enhancement. And then you stay there for a while and do cover some of the constructions of Joyce group in Oxford. Okay.
By enhancement, do you mean it's equivalent somehow.
It's not equivalent. It's embedded inside the enhancement.